Hey everybody, and welcome to Everyday Science. Today we're going to be doing a gel electrophoresis. Now you're probably like, what the heck is that? Don't worry, I will explain. So, I have been isolating DNA. If you look at some of my past videos, you'll see me isolating DNA from leaf tissue. And now I need to analyze it to figure out if it's good quality or not. So a way to do that is to use the gel electrophoresis. And so first we got to make our gel. Now our gel is going to be made up of a couple components. First, we are going to use agarose. Agarose is a type of carbohydrate that is similar to gelatin and pectin. And so it is made from seaweed. And so it's similar to the stuff that you would use to make jello or jam. And so I am going to be making a gel that is 0.8%. And so that means that I need to measure out 0.8% grams of my final volume, which is going to be 40 mils, which means we need about, whoops, so close, 0.32 grams. So I'm using a little electronic balance here. Okay, now that we have our agarose in here, so when I said it was 0.8%, that means it's sort of weight by volume. And so I am going to add the volume, so that is liquid. So we are using a type of buffer called TBE. It means it's made with boric acid. And so it is a basic solution. And so what that means is that it has a pH higher than 7. So let's see if I can do this one-handed. Ooh. See, this is what I do. This is how dedicated I am. And so we need to measure out 40 mils, so I need to take a little bit less. And then we are going to add that to our flask here and then melt it in the microwave. Hello. I realized I never described what a buffer is. So when I was talking about a buffer, this is a solution that has both an acid and a base inside of it. And so this allows the solution to prevent large changes in pH, either up or down. And so in our TBE buffer, we have the boric acid, but we also have this base tris. And so that keeps it at sort of a stable level, and so that's what we need for a gel. So a common buffer, for example, is your blood. Your blood has both acids and bases in it to prevent very strong or very quick changes in pH. Alrighty, so our gel is cooled down, and I have added a compound called ethidium bromide to this. It will bind to the DNA and let us visualize it under a black light or UV light, but it is toxic, so I have to wear gloves, and I'll throw these gloves away right away. So I'm going to mix it up, and then I'm just going to pour it into this gel tray. And so I've sealed the gel tray with tape. That's one of the reasons that I had to wait for it to cool, so that it didn't melt through the tape. And so I'm just going to pick up the comb. So this comb is going to create little tiny wells. And so if we look a little closer, so these wells are going to be what I'm going to load my DNA in after the gel solidifies. Okay everybody, so my gel is done. So I put it inside the electrophoresis chamber. So it's all set up, and it is submerged in the same kind of buffer we used to make it. And so what I'm going to do is I'm going to get my samples, and I'm just going to take out a little bit. So I'm only going to be doing 3 microliters, so very tiny bit. So you see, let's see if I can get it to focus. Oh, that little tiny bit of liquid. And so what I'm going to do is I'm going to mix it with a gel loading dye. Well, let's see if I can do this one-handed. Oh, yes. Yes. All right. And so this allows me to see it when I'm putting it into the gel. So what I'm going to do is I'm going to put it into the well and very slowly put it in. So there it is. And so I'm going to do that with the rest of the samples. So we're going to use magic. 1, 2, 3. Ta-da! All finished. Okay, so now that it's loaded, I have put the top on the chamber and I have plugged in the electrode. So these is the electro part of the electrophoresis. So this is a positively charged and this is negatively charged. Now, DNA is negatively charged, so it is going to run through the gel. So the gel has pores in it, right? And so since it's porous, it's going to run through those pores, and the speed at which it's run is based on its size. And so it's going to run towards this electrode. So what we're going to do is we're going to go up here to the doodad, and I'm going to set this for about an hour before I check it, and I'm going to set it to 110 volts. We want it high enough so that the DNA will run, but low enough so that the gel won't melt, because that would be bad. So if we zoom in, let's see if we can see the bubbles. See those bubbles? So that bubbles, these bubbles here, that is the electricity that's going through the gel. And so that tells me that the chamber is running. And so there's electricity running, and electrons are going from this electrode all the way through to this one. Okay everybody, so I've run our gel for a couple hours. And so I put it on top of this UV box, so it has a shield on it to protect me, and I want to make sure that I don't look at this without the shield, otherwise I'm going to get a sunburn and it's going to be no fun. So I'm going to turn off the light and I'm going to turn on the box, and there's our DNA. So each one of these sort of bands is the genomic DNA. And here I put a molecular marker. So these are pieces of DNA where I know their size already, and so I can compare my samples with these. And so since my samples are whole genomic DNA, they're going to be pretty big, so they're going to line up with the top of the ladder. And so that is because I explained earlier that the DNA is going to move from towards the positive electrode, which was in this direction. And because it has to move through the pores of the gel, the size will determine how fast it is. So the thing is any small pieces of DNA will run faster and be seen near the bottom of the gel, versus any big pieces of DNA will run slower and be near the top of the gel. And so I hope that this was educational, and if you have any questions, please put those in the comments and let me know. And then like and subscribe, and I'll see you next time. Bye-bye, everyone.